Hello everyone, welcome back to the open class. I am Desire, and today we would like to continue where we left off from the previous open class. So from the last one we were talking about multi-threaded executors, and we were trying to elaborate why our current setting was not working and why we had our job incomplete, basically. So today we're going to talk about in a bit more detail how to get code to start working, and then show a practical demo that's going to guide you in case you want to implement this on the robots. Let's say you've applied already on test on students, or you want to experiment with how to run module robots. So we're going to be diving into this to make that you understand, and I will do my best to at least give you some notion of why we were saying our setting wouldn't work and then how to solve it. So something, and I suggest you hang for the ride, and we will best get all the information in the hour. So one second here, and just give me 1 sec so that I can have this one closed. Alright. Okay, so this is what you must see, not the previous one. Okay, so just 1 sec. You should have the simulation loaded. As you can see, we have a student with a searcher, and if I can move myself a bit, I'll try to do that. So just bear with me here, but let me see if I can see the chat real quick. So if your project is loaded, or if the shared simulation is loaded, this is what you're supposed to see, right? And what I will do is I'll try to see if I can show how to visualize or how to fork the ROS by doing a real quick demo here. So if you bear with me just for a sec. So I have the project myself here, but so if you have the link, you should fork the ROS so that it appears in your My ROS, and then you can run it. For me, this is the one that we're gonna be talking about. So it's available here, and I can open it real quick. So since it's loaded, I'm not going to try to do that. However, be patient. The simulation is a bit heavy, but eventually when it loads, it must be visible like this. So let me check real quick to see if we've got the stream window showing in a different place. All right. Alright, let me check. Do we have it here? Yeah. Okay. Alright, I don't think I can see it just yet. Alright, so what I'll do is let's continue. So I'll just do my best to explain as much as possible, then we can make sure we make some progress on this one. So alright, so you should have a notebook that appears with your ROS. So for us, this is going to be the notebook that we'll be using, and when you fork the ROS, you should be able to see this notebook here. So what I will do real quick so that you can be able to see how to configure your own particular setting. So this is mine, and for those who would want to have a different configuration, you can go here and then drag the windows the way you like it, then save as custom layout, right? So normally you may have something like this where your simulation appears here and every other stuff appears like this, right? So you can play around to just set up the simulation the way you, the window view the way you want. I prefer to have it this way for me, so that I can be able to see the simulation at once and the notebook at once, and we can be doing things in the terminal, right? Okay, so for the time being, I'm just going to maximize the notebook, and so that we can at least be able to see the general idea that we want to visualize, or we can be able to see things that we'll be going through. So first of all, you just have the images here so that you know that it's going to look like that. However, it is very important for you to have taken one of our free courses, C++ for Robotics. This is going to give you a platform to be able to understand the code that we'll be going through. So we're not going to do as much on C++ details, but what we will do is to understand ROS2 within the context of someone who's writing ROS2 nodes using C++, right? So you will have to bear with me there. What I'll do is I will do my best to make sure that I can give you a rough idea of what the C++ things that may be unfamiliar. So for now, let's try to understand the problem real quick, right? So what I'll do, let me resort to my usual setup, and I will go into, as you always know, I like using the terminal, so that I'm hoping you also get used to this way of working, because we cannot run away from this as roboticists. It's very important for us to be comfortable in the terminal. So what I'll do is, let me navigate to the src directory, and then I'm just going to list the contents here. So I have the executor demo, which is going to be our main package that we'll be working with here. So you can see we're going to create it here. So what I will do is I'll remove everything so that we start all from scratch, right, and build it step by step. And you can be seeing part of the things that you need to know in order to progress as a ROS developer. So what I'm just going to do is I'm going to call rm and then rf. So if I was removing just a file, I could just call rm, right, remove, and then it will be deleted, right? But because I'm deleting a folder, right, I have to use rf, so the flag r and f. So f of course, r for recursive, so that it deletes everything that is in that folder, right? So, and then I'll type the folder that I want to delete. So this is the package that we're going to remove. So once you do that, it will be deleted. So if I list again the contents, you will see that there is a no more executor demo package, right? So after this, we're gonna start everything from beginning, right? So what we'll do is, let's just walk through some of the things that we will do in this case, because we want to show what would happen when you're using a multiple callbacks in one thread, right, using the default way of doing things. So what I'll do is I'll create the package first, put the script on VS Code, and then you can be able to see, okay, this is what it looks like, right, so that we can compare what we see, right? So let me check something quickly here. Can you see me? I see my cursor is moving, but I think I've got a little bit of difficulties with visuals. Okay. All right. Okay, so let's just maximize what we've got here, and just so we see. So this is the code that we're going to use as a demo for just showing what multi-threaded executor setting will look like, right? And I'm gonna try my best to show how you notice the behavior that this is a multi-threaded executor, because you can see when we spin our node here, or in the main script, when we call rc or cpp spin node, we don't specify any executor, right? So the default way things will happen in ROS2 is that everything else will be assigned to a mutually exclusive callback group, right? So we're going to talk about this as well. So we want to understand what is a mutually exclusive callback group, right? And would want to understand how does that group relate to callbacks in general, right? The normal callbacks that we know, the ones that we call whenever we get a new message from a LiDAR scan subscription, for example, or the one callback that is responsible for publishing a command file, right? For example, because callbacks do a lot of things, right? They don't necessarily need to be publishing something, or they don't necessarily need to be doing things that we can see. However, the fact that it is a callback, it means that it's something that executes frequently upon receiving a particular ROS message, right? So subscription and publishing, it's a standard principle in ROS 2. So what you're gonna do is, let's create this package, right? So everything that we'll do will be in our executor demo package, right? However, the variation will come in the scripts that we'll be using in there. So let's go here real quick and we can start. So once you have navigated into your ROS 2 workspace, so here at the construct, everything we do will be done in a ROS 2 workspace. However, as I've said from previous classes, you may have other workspaces, right? You may have an AI workspace, such as AI_workspace. You may have notebook workspace, for example, right? So, but anything that relates to ROS 2 must be in a ROS 2 workspace. Okay, so let's go ahead and create our package. Just one sec. Okay, so if you copy this command in the notebook, so I will paste it here and then explain to you a bit more what's going on, right? So here we are calling the ROS 2 package create command, and then this is the name of our package, right? So you can have any other name of package here, right? And then we have our build type flag, right? For this one, because we are creating C++ packages, our build type is called amend CMake, right? If we are creating a Python package, you will have amend Python, for example, right? And then we specify the dependencies, right? So dependencies, these are libraries that are native to ROS 2, or if you have compiled your own and managed to link them correctly, you may have your libraries that are available ready for linking with your package that you're currently developing, right? So, but in general terms, what you have here are ROS 2 packages, right? So we have an RC or CPP, the client library itself. This will make the C++ tools for ROS 2 available to us. And then we have the sensor messages package. This will make also available the ways of working with sensor messages via the C++ RC or ROS 2 client, let's say that. And then we have geometry messages as well, which we will be using, right? So as you will see in the scripts that we will write, there is going to be a use cases for these, right? And I'll try to highlight them as we go. So let me just check something real quick here to see if I think my screen is visible, but there is something with the image of myself. Can you at least hear my voice? Let me check real quick with Sonia here. Alrighty. Alright. I think let me switch to the host view one time, and then this one is alright, so it's just the camera issues. Okay, let's try again. And then alright, and let's go back one more time just to see if this works for us. Okay. Alright, I think if you can hear me, I'm better off progressing so that we don't waste valuable time here. I think it's more important for you to hear and see my screen than to see me. Okay, so let me go on here, and then we can have this issue fixed in the next open class. Okay, so going back to what we've been talking about, right? So once you've copied this command into your terminal, you can press enter, and then you will have the package be created, right? And if you list using ls, the ls command, if you list the contents, you realize that, okay, you have got now an executor demo package, right? So the package has been created for you, and there are also some extra files that has been created for you, right? I will not get into as much detail about this because we've got a lot of stuff to go through, right? So what I'm just going to do is I will be doing things, and I'm hoping you will be seeing what I'm doing, and given the details that we have spoken about in the previous open classes, you will be able to understand why I'm doing these things, right? So what I'm going to do is I'm going to navigate to our executor demo to create a single threaded monitor.cpp a script, so that we can just demonstrate real quick some of the nuances that we want to speak about, right? So after this, I will go into the src folder for that package. Then I'll use the touch command to create this script real quick, right? So for the sake of time, and also to minimize the errors that we've got, I am going to paste here the name so that we have it as exactly as possible. And then let's open the IDE, and we're gonna navigate to our executor demo package, and then add the code for this script, right? And this is the code for the script. So how you can edit, you can just Control A if your cursor is in that cell, Control A to highlight everything, then Control C, and then you come here, you open that script, and when you have opened the script, you can just use Control V, right? It will paste everything for you there correctly, right? So you could use the copy button, but sometimes it introduces foreign characters, so you want to be careful if you're using it, just to make sure you don't have anything that will cause your program to not compile, right? And then, so with that having done, let's just make sure we add the statements to the CMake list that will allow our executable to be created and also to be linked when we call conbuild, right? So this is what we're going to do. We're going to go to our CMake list, and as usual, we're going to add it after the end if here. So we are adding our single threaded monitor node. That's the name of the executable itself, right? So you realize that the name of the executable and the name of the source file, they are similar but not the same, right? And the name of the executable is the one that is required when the linking process happens. That's why you see here we use single threaded monitor underscore node when we call amend target dependency, so that it's linked to the libraries themselves, right? And then once we've done that, then all the things that we require in the ROS client library for C++ and the sensor messages will become available to our executable, right? Because they have been linked together, right? So, and then here we just install that executable in the library, right? So that it becomes available for us to call it using ROS2 run, for example. And as you will see, that's what we'll do. We're not going to use any launch files in this one. So once that's done, you can copy this. So this will navigate to the ROS2 workspace where we should always be building, right? So you don't build anywhere else. You always build in the root workspace, right? So in the ROS underscore workspace, that's where we'll build. If you have got your workspace named in some other way, like maybe my workspace underscore workspace, you want to compile there, so that you don't confuse yourself, or you don't confuse the way ROS2 libraries in packages compile together and make their dependencies available to each other, right? So for now, that should be a good enough explanation, and if you want to dive deeper, you can maybe read the documentation about why we need to always be compiling in that workspace, right? But it's good practice, right? It's good practice even if you don't understand as much. So once we have sourced our workspace, we're going to run this, right, real quick. So we're gonna run this single threaded monitor here. Before we talk about it, we're just going to run it to see something. So they are very subtle things, however these things are the foundations of what we will want to understand in the coming bits of this class, right? So the first thing that I want you to note is the order in which the processing is happening, right? You can see every time you've got processing 1, 2, and then 3, right? So this is just to show you that there's a particular order of execution that's happening, right? So what I want to do is, let's move the robots a bit in the simulation just to demonstrate that you have something happening as this node runs that's in correspondence to the topics that we're getting from the simulation, from the robots themselves, right? So, and what you're going to do is we're going to try and run this on connect to the real robot, but for this one you may have other topics that are not be published because only one robot is running at the moment. But however, for the board box you get 3 robots, right? So the fastboard 1, fastboard 2, and fastboard 3. So what I'm gonna do is, if you tap on the simulation window and you use your mouse to drag, you can drag until you see this planar view, right? And then what you have to do is you tap on each one of the robots, right, and use the arrows, right? So if you use the arrows, you can see that the robot is moving, and because this red one is our fastboard 1, so it's the robot 1, right? So what I'm gonna do is I will do my best to move it as close to the wall as possible, and I want to look at the data that we're getting from our from what this what this node is giving us as far as the closest thing to our robot, right? So if you look at robot 1, it's saying let me stop this real quick so that we can go through the logs, right? So here we've got robot 1 scan giving us a minimum distance of 0.28 meters, and then robot 2 scan giving us a minimum distance of 0.23, right? So what's happening is that our LiDAR scan data is being processed all around. So it's not that the robot is looking only at the forward and giving you that, okay, the nearest distance as far as my front is concerned is so much, right? The processing that is happening here, if we look at the code eventually, is that our LiDAR scan data is being run through every cycle. So every time the callback is called, it runs through all the ranges data and tries to figure that, okay, of the ranges data that I'm receiving on topic 3 or fastboard underscore 3, right, this is the closest obstacle, right? Whether it's in the front, left, right, or back, that doesn't matter. What matters is what is the minimum value of that ranges data, right? So what I'm gonna do is, let's do this, right? So let's move the green robot to a different place, right? And if it will allow me to move it, give me 1 sec, or slightly more. Okay, so for some reason it's not responding. All right, but no worries. I think for the purposes of what we want to show, our red fastboard will work, right? All right, so okay, let's run through the code a bit, and I will open this single threaded monitor, right, and then now try to explain a bit. So what we wanted to do, right, in this one, I just wanted to show what the current setting, or how you develop the generic ROS2 node, right, without thinking about executors or anything with related to multi-threading, right? So what you would do is you declare your subscriptions just like this, right? In this case, we have created 3 subscriptions, right? So each one of our subscribers is subscribing to a different topic, and we have got a separate callback for each one of them, right? For fastboard 1 scan, so remember, this is the data that you will get from the red robot. The red bot is the one that we call fastbot 1, right? Fastbot 2 is the green one. So if we pull up the simulation right now, this green one here, you see there's a 2 on top. That's the fastbot 2, right? So the subscription to fastbot 2 scan will receive LiDAR scan data from that robot, right? The same applies to fastbot 3, right? It will also be getting values from on the fastbot 3 scan topic, right? And it also calls a separate callback, right? So if you look at each callback does the processing of finding a minimum distance, right? So if I would highlight this real quick, so we've got float mean distance, right? So find minimum distance given the message, right? However, what I want you to understand is that the find minimum function is common among these callbacks. However, it's used in different it's used by the callbacks, right? So what you should think about when you say this kind of behavior, it's like there are multiple instances of this function that are created for each separate callback, right? However, because this is default behavior for ROS2, what that means is that you will have one of each, right? So if a scan callback 1 is the one that's called first by virtue of it being declared first in the constructor, right? That means the order of execution will always be scan callback 1 first, scan callback 2 after that, and scan callback 3 after that, right? This is the default behavior, which is called mutually exclusive behavior. If you're going to think about it in terms of callback groups, what it means is that ROS2 is assigning, or the ROS environment is assigning a mutually exclusive callback group by default, right? It's assigning all these 3 callbacks to the same group and forcing them to execute one after the other, right? And part of the way in which you can find out that this order is being ensured is by noticing that the order of execution is always the same, right? So if we open our terminal, you can see that it's always 1 2 3 1 2 3. So that means you will have the scan callback 1 be called first, scan callback 2 after that, and then scan callback 3 the moment after that, right? And this is default behavior, right? So what happens though, the question you might be asking is, okay, what happens is if you have got this callback taking a lot longer than all the other ones, right? That means then you run into problems, right? Because it means callback 2 cannot run if callback 1 is not finished executing, right? So then you end up in what we call a blocked state, right? You end up having one job blocking the whole pipeline, right? And that is the purpose of a multi-threading and reentrant callback groups, right? So this is what we are going to be talking about. This is what we want to understand given this limitation that we've got, right? So this current setting does not have as much work happening. So if you look at the function that's being called to find minimum distance, which is the function here from line 68 to line 76, right? This function is relatively light actually to line 78, right? It's relatively light for the things that are happening. It's fairly light, and given that we are in simulation where everything is predictable, it can be considered light enough to ensure not ensure blocking behavior that we can see, right? Because even if it's happening, it's processing so quick for us that we think, yeah, okay, there's no blocking behavior whatsoever, right? However, understand that depending on the size of this job, right, you can get into cases where once the first callback is called, the coming 2 callbacks, in this case, because the 3 of them, the following 2 cannot execute because that job is going to take so long. So what you want to do is to assign it to a different thread, right? Because by default, what we have right now is we have default behavior. Even if we have not specified that we want a single threaded executor here, or we want a one executor, i.e. one thread, ROS2 does that for us by default and assigns all the callbacks to a mutually exclusive callback group, which forces a order of execution, right? So depending on who is defined first and called first, that order will be the same until we terminate the node, right? So let's go to the next stage real quick, and we'll see if we can get different behavior. So take note of this. Let me highlight this, or maybe run it one more time in this full view, so that we can have something to refer to when we are trying to compare it to a reentrant or multi-threaded executor running. So I'm gonna clear this and just run our single-threaded monitor real quick. So if you're going to think about it, if you had to run something that requires a constant update, like every 2 seconds, if you have a job that blocks that, then you will not guarantee that your execution will happen the time you want it to happen, because the job might take longer in some instances or take a lot less time in other instances, right? So what we've got here, so that we just have this terminal for our records, right? So you see there's robot 1, robot 2, robot 3, robot 1, robot 2, robot 3. This is the order that I'm talking about. And for each one of them, you can see that for robot 1, let's look at robot 1. Robot 1 is saying the minimum distance in its ranges data is like 0.6. Robot 2 is saying it's 0.3. And robot 3 is saying it's 0.3, right? So what might be happening, because we did not move this, or at least they're not responding to us at the moment, is that they're probably seeing each other as the closest thing to them, right, to themselves. So they register each other as being the closest obstacle, right? And if you'd allow me to zoom, yeah, you see, so they are very close to each other. If we're not counting this wall, I think it's being missed completely. But yeah, that's the current setting, right? And this one that we can move is I would have wanted you to see what happens when we move it. So let me just do this real quick and run it one more time, then try to move the robot, right? And if we move this spot by clicking on it, okay, so you should be able to see that LiDAR scan data for the first robot must be changing as we move the robot. Yeah, you can see here mean distance. Whoa, mean distance 0.84 for robot 1. And yeah, there's a lot going on here. Let me just stop this real quick and try to scroll up so we can have a look. Okay, so yeah, this one, mean distance 0.84 meters. So as you move the robot, your processor, the callback, will keep processing, right? Will keep trying to figure out what is the minimum distance, right? So when you are trying to implement some type of obstacle avoidance behavior, this is part of the implementations that will be used to check what is the closest obstacle, right? So let's go to a multi-threaded executor real quick and create that, then we will talk about it as we go. So just to illustrate some steps here, so if you'd allow me, I'm going to maximize this and we can at least see some of the steps. So what we want to do is we want to create a multi-threaded executor, so we're going to put that in a multi-threaded monitor script. So I'm just going to copy this so that we can create this script in our SRC folder. And then, so what we're going to do is we're going to use reentrant callback groups in multi-threaded executor, and I will specify why you need reentrant callback groups, right? Because remember I said by default everything happens in a mutually exclusive callback group, right? In ROS 2, that's the default behavior. So let's create what we need to create for now, so that we can do a brief demo before we run it. So I'm gonna leave this terminal as is because I wanted to hold our records for what we've been doing, and I'm gonna switch to terminal 1. So I will navigate to our executor demo, the SRC folder, then list, and we have this. So we're gonna create another script in here and then call it that, right? Then let's open the IDE real quick and then copy and paste the code that we've got here. So we'll come back to this and talk about it a bit more. For now, let's put everything in the script and then we can run through the explanations quickly. Okay, so I'm gonna paste this in here, then we want to compile it, and so to compile this one, we have to do the same thing where we add our executables, compile our code. For this one, we're gonna use a launch file. So let's create a launch file first, just to stick to the order. So what I'll do is I will create a launch file. So some of these fundamentals, they are in the previous class. However, it's important that we always create our launch file in the package. So this is our package directory, right? This is our package. So the launch file is contained with the other files that are created by default. So the CMake list is created for you. You just have to edit it. The include folder is created for you. The package XML and the SRC, they are created for you every time you create a C++ package. However, the launch file, the launch directory is not created for you. So what we have to do is to make directory, right? So mkdir, shortcut for make directory, or the command itself, right? So you have to use mkdir, and then you specify the name of the directory you want to make. So by consensus or general rule is we always call this directory launch, right? And this is where all the launch files will be found. So if you navigate to that directory, and then you use the touch command again to create the launch file that we want to create. So our launch file is going to be called multithreaded launch.py. So let's copy this name and add it to, and yeah, so paste it here. Now we have got our launch file. So what we will do is just copy the launch script itself. If you do not understand some of the specifications or the lines of code that are here, I highly recommend you look at the previous open classes. We go into detail about what we're doing. So the package name, and then the executor that you want your launch file to actually call, and then the output, which is the screen in this case, because everything is happening in the screen. So let's go and add these details to our launch file. So if you navigate to the launch file here, multi-threaded monitor, you paste those, and then now you have got your launch file with the stuff that you need. So, and then this we are going to add now. So you realize that the difference with this implementation or this addition to the CMake list is that what we have added instead is that we have also added a call to install what is found in the launch directory, right? And it's going to be installed in the shared folder. So that's the one you found. I'll show you real quick where you find that. Let's first do the modification so that we understand what we're doing. So if you look at this, we have install targets. That's installing our previous executable, right, and the current ones. So there is no need for you to have this. So what I'm going to do is, to make sure I don't confuse you, I'm just going to remove this real quick, right, because the single threaded monitor is also being included in the one command that I've copied here. However, for the linking and creation of executable, right, you still need to keep the previous one, because here we're just adding the one for the multi-threaded monitor, right? And then we are adding this. So this was the one that we were not adding in our earlier implementation, because we were just calling ROS to run. We were not using launch files. But if you're going to use launch files, you need to install the launch files and make them available within your ROS environment when you compile, right? So now that that is done, let's compile and run our code. So compile real quick, and then we will run it and try see what is the change in behavior, right? That's what we want to say. So it may be very subtle with regards to this, because there is not much that each callback is doing. However, keep in mind that if that processing or that process of finding minimum distance, if it was anything that would take 3, 4, 5 seconds, you will begin to see differences in how quickly the results are brought back to the terminal, right? Because each one of them will be executing in parallel this time around, right? Unlike the one that had to wait for the other to finish, right? Because they have been assigned by default to a mutually exclusive callback group, right? So let's run this and see differences, right? What I like the most about this is that even though it's so simple, you will be able to even tell that things are happening in very different order and so quickly, right? Okay, so let's run this. I'm going to make this full view so that we see what's going on. So I'm gonna clear and run the multi-threaded node, right? So now that it's running, you can see that there is some order, but the order is lost because everything is happening on its own in a different space, right? And part of that, if I press Ctrl C here, if we look through every line of the logs that we're getting, right? So let's look at the first status report, right? So if we look here, so we have processing robot 1, processing robot 3 scan, processing robot 2 scan, and then back to 1, then 3, right? 2, 1, 2, right? 1, 2, 3. Now the order is slightly different. 1, 2, 3, 1, 2, 3. For this one, it seems like the order was kept. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. The same applies here. But bear in mind that the job that's being done is very small. But you can tell, right? The nice thing is that you can tell that everything comes at once, right? So if we go back to our previous terminal where we were calling a single threaded executor, right? And we run it one more time like this, right? This shows you that the work is coming in a particular order. It's unlike the multi-threaded executor where everything just shows up in the terminal just like that, right? So there's proper multi-threading going on there, right? And that's the benefit of having callbacks that are running on a separate threads, right, via the use of reentrant callback groups, right? Because reentrant callback groups is the only group. So there are two groups: a mutually exclusive group and a reentrant group, right? Mutually exclusive, this is the default one, which says do or execute callback 1 after 2 after 3, right? So there is proper order there. The other reentrant callback group will use the available threads to the best of its ability. So what you do is, if you have 3 callbacks in a reentrant callback group, what it means is that because they are in a reentrant callback group, if you specify that you want a multi-threaded executor as well, the reentrant callback group itself will say, okay, each callback of those 3 will run on a separate thread, right? Because what you want is parallel. You want parallel work. You want everything to happen at the same time, right? And as a result of that, that's why in the terminal we are seeing values appear at the same time, because it's using the available threads to the best of its abilities, right? So the other thing with multi-threaded executors is that you can also specify what number of threads you want it to use, right? So for example, if you know that your system only has got 2 threads, you can also limit it to 2 threads. However, if you give it 3 callbacks, right, if you give that reentrant callback group 3 callbacks, right, and your system is limited to 2 threads, what it means is that of those 3, it has to make the other 2 follow each other, right? Because, or it has to juggle, depending on who finishes first, gets the other callback that's waiting to be processed, right? So that's a very important thing to know. So let's minimize this real quick and try talk in more detail what's going on, right? So there are 2 things that I think are very important for us to grasp in the current situation, right? So the first one is that if you have a mutually exclusive callback group, right, if we have 2 of them and you use a multi-threaded executor, right, and you assign those two to a different, let's say, you use a multi-threaded executor, right, but you assign each one of them a different callback group, right, there is potential that you can get parallel work happening, because if you're using a multi-threaded executor and you give it 2 threads, right, there is no reason for the executor to not assign each callback group to one. However, when you try to have more than one callback in each of those mutually exclusive callback group, then even though they are assigned to a different executor, or even though they are assigned to a different thread, the order is still ensured for each group, right? However, relative to each other, because they're in different callback groups, right, there will be variation because they are in different. So this will be something that we'll talk about as we get to our last demo. So what I'll do is, let me open this multi-threaded monitor real quick, and if you'd allow me to check something here. Okay. Alright, so let's start from the top for this one, because I think what we're going to talk about is more visible here. So what we did here, because we want proper multi-threading, right, we had to create a reentrant callback group, right, and the process of creating that group happens here, right. So here we are specifying that we want a scan callback group, right. So what it means is that of the 3 callbacks that we have for each scan topic, we want to assign them to this group, right. So this is the creation of the group, and we call it reentrant, right, which means we want it to be a multi-threading capable, right. So we create a group here, right, and we call it a scan callback group, right. You also note that it's an internal variable, right, for our node. That's why you see there's the underscore at the front, right. And then what we're doing is we are creating options, right. So the act of creating an option is like, okay, you are saying I want to create an available variation of a particular executable, right, or of a particular let's say callback, right. So you want to have the ability to pick and choose how you assign this callback to the different callback groups, right. So this is very important, right. Otherwise, if you don't declare this, you will figure out that it will become very difficult for you to then assign each callback to a particular group. So what you see that is, after you have created your options, right, you always use the option to specify where each of the subscriptions must go, right. So if in this case you have got what you call subscription options 1, right, if you are doing some publications, you have different options, right. So in this case it's a subscription option, right. So you call it option 1, and to option 1 you assign this particular subscription, right. So this is considered to be the first possible job for this reentrant callback group. And then what happens is that in the second one you also assign it to option 2, because you want these things to be able to run in parallel. So what you do is you have to assign them to different options, right. So in this case you are also saying, for the subscription to fastboard 2 scan, I'm going to assign it to option 2, right. And then the third one is for option 3, right. So you're assigning it to option 3 because you're saying, okay, this is the job that will be done on data that's coming from fastboard 3. And then after that you create a timer, right. This timer here is happening also separately, right. And you must also bear in mind that the timer itself, because it's something that happens as per cycle, it can also be assigned to a callback group of its own, right. So you should not limit yourselves to just subscriptions or to just publications happening on a particular thread, or on a particular, let's say, in a particular callback group, right. a timer itself, because it's something that runs in a cycle, it can be part of the jobs that are supposed to be executed within a particular callback group, depending on whether it's mutually exclusive or it's a reentrant, right? So let's look at what's happening. So each callback again still has its job. It's the very same job that it was doing, which is finding the minimum distance, right? So however, the way each one of these runs is it runs in a separate thread, right? Because we have declared a reentrant callback group and we have created these options for ourselves, which is a way of declaring the different types of jobs that are supposed to be assigned to each group. So within each group, a job is seen as an option, right? It's something that it can do, right? And that's why you see that if one finishes before the other and you've got a limited number of executable, right, it can always pick. There's no order that, okay, option 1 will always go first or option 3 will always go last. No, it's just a possible route that your executor can take, because it can say, okay, I want to do this job because the one that I was currently doing is done, right? So I want to assign it to this thread, or I want to assign the next job to a thread 2 because thread 1 is still busy with something, right? That's why it's an available option there. So this is being done in a multi-threaded fashion, and part of the way that is done is you declare an executor. Yeah, you declare multi-threaded executor. So what this means is that the ROS2, the underpinnings of ROS2, like the things we don't see, the things that interact with the operating system, those are the things that will figure out, okay, I have been told to use a multi-threaded executor, therefore I have to find the maximum number of threads that I can use given what the operating system is giving me, and based on that I have to call each of the separate executables on separate threads, because I've been told to do this concurrently, right? Unless I run out of threads to use, only then will I have to chop and change between which thread each group or each callback will be running on, right? So this is what is basically happening in this script, and what is important here is that if you remember what I've said, you can also give it the number of threads to use, right? So if you remember from our previous class, there was the code spec that was also showing that, okay, you can actually specify that you want 2 threads, right? So even if your machine has got 18 threads, 12, 6, 8, 2, you can even specify, right? Remember, you can only specify to the maximum capable, right? You cannot say, okay, because I have 2 threads I want to have 4. No, it's hardware dependent, so it's an important thing to know. So let's go to the last example real quick, and we'll try to explain a bit more about mutually exclusive callback groups, because this one was purely on reentrant callback groups and having work done in parallel. So let's run through this real quick as we are losing time. And what I'm going to do is I'm going to create this separate groups monitor, and I'll try to explain what's going on as always, so that we see the differences, right? They're probably going to be very subtle. However, every time you see mutually exclusive, always think my work is going in order. Each thread, even though they are both running mutually exclusive callback groups, what is within them is what's forced to go in a particular order. However, the order is not dependent on a separate mutually exclusive group, right? Each group is responsible for managing the order of its own callbacks on its own. There is no dependence on what the other is doing, right? So they are completely independent, completely disjoint, and it is very important for us to know that we can control execution for a particular group. We can control the order of execution for the group itself, but we cannot control order of execution in between groups, right? So from one group to the next, we cannot control order of execution there, right? That's completely separate, because it's like one thread runs its job and the other thread runs its job, and the order in which each thread does its job is completely independent of what the other thread is doing. that's where we're trying to get to here. So let's create this real quick, and then we can run it. You'll probably not see as much difference, but the principle that we want to show is very much clear when you look at the code. Okay. So let's create our separate groups monitor, and I will stop execution here in each one of these, and let's clear. So let's navigate to the executor demo and src package, then not package. Alright, so let's create a script. I'll go separate groups monitor, and again I'm gonna use touch here, so and create separate group. Then let's open the IDE. So again, just highlight, Control A, Control C, and then we can add everything to our IDE. So maximize, and then separate groups monitor here. So I will paste this and then talk about it after this, right? So let's go through the compiling process one more time, so that we have this working at least, right? And again, you see that we have all the executables, so I'm just gonna copy this, and I'll just make a minor modification to CMake list by adding that and removing the duplicate. So okay, and here, so okay, now we have everything. So we have added all the 3 executables, so you can run them in different terminals and be able to see what's going on, right? And okay, but remember, it's hardware dependent, so this is very much a strong limitation. You have to understand that despite the fact that you're doing it in separate terminals, your hardware is the same, right? So you have to think about these things when you are executing this. You're trying to generate something similar on proper power limited, processing limited hardware, right? For some particular machines, you may not see anything because maybe you have got more threads than you need, right? So let's compile our code real quick and run it. Okay, so we're gonna go, as always, navigate to the workspace, then compile. And we're gonna, because we didn't create a launch file, we're just going to use ROS to run after it's been installed, right? Alright, so let's run this just to see. Right, separate group started, and this time you're using mutually exclusive callback groups. So because they are mutually exclusive, right, but they're running on separate threads, right? So that's why you get similar to reentrant behavior, right? But the difference is very important. The difference that's very important for us to understand right now is that in each mutually exclusive callback group, right? So let's look through the code and be explaining while looking at examples, right? So what we have with this one is we have 4 callback groups, right? So remember, for the mutually exclusive, for the reentrant, right, we had 1 callback group, right? 1 callback group. But what was happening is that because it's a reentrant callback group, each callback you assign to that callback group, right? Here, this is what I'm talking about. Each callback that you assign to this reentrant callback group can have a separate thread for itself, right? The same applies is happening in a separate groups. However, in this setting, what is happening is that it's not that each thread is running a particular callback. It's that each thread is running a particular group. So in addition to each of those groups, you can have more than 1 callback. But what's important is, once you have more than one, there is no parallel work going on there. Within that group, at least, there's no parallel work going on. Each callback in that mutually exclusive group will have to follow a particular order, right? So what that means is that if we have 4 mutually exclusive callback groups, right, and we are using a multi-threaded executor, as I've said, and your machine has got more than 4 threads, or at least 4 threads, what it means is that each one of these groups will be running on a separate thread, and as it runs on a separate thread, it can also have more callbacks added to each one of them. But once you have more than one, right, you cannot have parallelism within a group. You can have parallelism from group to group, but not within a group, right? This is what's going on here. So what we're doing is, we have got our callbacks, right? So our callbacks, these are subscription callbacks, right? So every time you get data from fastbot scan 1, for example, you have it in option, let's say option 2, right? And option 2 is assigned to a mutually exclusive callback group that's called callback group, a scan callback group 2, right? So that means that the subscription to fastbot 2 scan will run on a separate thread in a mutually exclusive group of its own, right? The same applies to this here. It will also run in a mutually exclusive group of its own. And the reason why we have 4 here is we are also separating the group for the timer, right? That means the timer will run on a thread of its own in a mutually exclusive group as well, right? So what it means is that these 4 things can happen concurrently, but once you have other things happening within each of those 4 groups, right, then there's no parallelism going on there, right? So it's very important for us to understand this. Mutually exclusive callback groups, they restrict the order of what happens within themselves. However, if each mutually exclusive callback group is assigned to a separate thread, then whatever is happening within them can happen in parallel relative to each group, but not relative to the contents itself. The contents in each group will still run one after the other. It's just that each grouping can have things happening in parallel. That's why you get like multi-threading behavior when you run this code in the terminal, right? So that is that for this bit. What I want us to do is to try and maybe connect to the robot and see if we can have fastbot 2 and 3 topics showing. But for this one, because we're using simulation, right, we have got fastbot 2, 3 showing, so it will work for simulation. However, if fastbot 2 and 3 are not on at the moment, which I have to check, by the way, we may not get the same code to be giving us the same results, but it's good practice. So let's do that real quick. So if you would allow me to try and connect here. Okay, so we're just gonna connect to this one for now, because that's the one that is available for our usage. But this applies to all the fastbots that we have in our bot box, right? Because they all they have publications to the to the respective topics. As you have seen in the simulation, remember, it doesn't change, right? You can transfer this onto the real environment as long as you have it configured in exactly the same way. So it's a very nice thing to have. So let's try to connect, and we can at least check if we're receiving data from the fastbot 1 robot, the real robot itself, right, not the simulation, and then get some information about, okay, do we have something coming from the others? No. And how will our code react to that? Okay, I think we might have a bit of an issue. Alright, let's wait for it to connect. Alright. Should be connected. Alright, one more sec. Let's see. Alright, it looks like I'm completely out here, but I'll try again. Check and then connect. Okay, let's see if the bot displays. Yeah, okay, so let's just do one small thing. Let's try to move in. Oh, and the other robots are not there, so alright. For fastbot 1, everything will work, but for the other fastbot 2 and 3, not as much. So but that's fine, the principle is the same, and you can very much do exactly the same thing that we did. Let me just run ROS to topic echo so we can see. Let's do topic list for now first. We want to see the available topics. So we've got fastbot 1, fastbot 1, fastbot 1, right? Remember, in simulation we had fastbot 1, fastbot 2, and fastbot 3, right? So if we try to run our any of our multi-threaded stuff, right, we'll get information for fastbot 1, but for fastbot 2 and 3 we won't be able to get that. So but that's fine, the principle is the same. You won't have to change anything. What you just have to make sure is, when you now have all of them there, if you're using fastbot, for example, if you have acquired the bot box for yourself, is that the same stuff that we're seeing in simulation is the very same stuff that you see on hardware. So it's very, very impressive to know that we can transfer what we've done in simulation to the real environment, right? However, the nuances will come into play, right? You can be able to see that, okay, maybe I'm not getting data in the order that I was getting it when I was using like a mutually exclusive callback group, right? Because now probably there's some genuine lag that's going on with the hardware itself, right? Then you begin to see the importance of, do I have to do multi-threading? Do I have to split these things so that they run in separate threads so that they don't block each other, right? So it's gonna be very interesting when you try it out on the real hardware, because the simulation kind of spares us from seeing these things, because there's perfect timing, there's perfect synchronization of subscribers and publishers generating information, so let's have a look. Let's just try to run one of them, right? Why I'm doing this is because we just wanna see, right? We just wanna see if we get this data coming through, and what does it do for the other fastbot 1, 2, 3 topics, right? It must be able to tell us, okay, there's no information coming from fastbot 2, right? So what you see is that, okay, there's only processing for a fastbot 1 that's going on, right? So if you look here, it's only information from fastbot 2 from fastbot 1 that's coming, because that's the only publisher that's available, right? However, if we had 2 and 3, for example, you get the same information. So if we try to move our bot, so I'm just going to do teleop here, and ROS to run teleop twist. And you have to remap because you're not on command file. ROS args. We want CMD val to passport 1. So we're just remapping here the topic because the passport 1 command val topics have been namespaced, right, to allow to prevent conflicts between the topics for each of the passports that are available in the BotBox warehouse, right? So when you press enter, then let's minimize this to try and move the robot a little bit, and then we can be checking what's going on relative to the distance that's being published, right? So if we look at this, minimum distance is 0.71 meters, right? So let's move it front or back and stop. Okay, and then we check. Okay, now you have 0.18 meters. So you see that our callback is working, right? Is working as expected because now the values do change, right? However, as per the principle of a multi-threading that we would have wanted to demonstrate, right, it's not very much visible in this case because we don't have like the multiple passports in the current setting. But remember, as I've said, this material is basically transferable to the real environment, right? What's important is that it's there for your use, right? So, and the other thing to note is that you can see that it's saying minimum distance is 0.21, right? Clearly, the distance from the front to the here, it's greater than 0.21. So this is what I was saying when I was saying our algorithm in this case, it just runs through all the ranges data and tries to figure out where is the minimum distance, right? It doesn't care it's in front, back, rear, what. So it's important to understand this as you make use of this code on and on and on, right? So I just wanted to show that, and when we have all the other passports available in this current setting, maybe we should just do another short live class demo so that you can see that it's very much transferable. But I'm sure if you've been following our open classes, you will see that the stuff that we do in simulation, it works on this hardware setting, right? Which is very good, a very good learning platform. So you can get a bit more detail if you go through to the bottom of the notebook about the things that are included. As always, right, your panels, your 3 passports, and the warehouse flow setting. And you also notice that each one of the passports that you get with the BotBox warehouse has got a gripper on it. So you definitely have got more things you can do with this, right? And you see there's a camera there on each one of them. So it's a very good learning platform for both general robotic stuff and ROS 2 stuff, and also trying to implement some form of AI and perception. So it's a very good package, and you also get the blocks where you can have a gripper go and grab those things and move them to a different place, like what's happening here. You also get the arm and the conveyor belt. So this is very good for educational purposes. You can practice manipulation, you can practice just navigating, right? Having each of the passports navigate the environment, avoid obstacles, and get that block delivered to, let's say, the conveyor belt, for example. So very, very good platform for practice and learning. Okay, so yeah, that is that for this open class. I hope it will enlighten people who have been worried about what is multi-threading, how do I get to work with the current platform that's given by mutually exclusive callback groups, or with the platform that's given by reentrant groups. So key things to remember, right? Everything in a mutually exclusive callback group will run in a particular order, and that order will not change, right? All the things that are in a reentrant callback group, they run in separate threads concurrently, given that if enough threads are available, right? Otherwise, some of them might have to follow the other, but you cannot ensure order, right? That's important. So, and another important maybe meta topic is that if you have mutually exclusive callback groups run on separate threads, then you have got their work happening in parallel, but the work that is contained within themselves is not happening in parallel. There has to be some particular order that's ensured. Okay, so that's that for this open class, and I wish you all the best until the next one. I'm so sorry you couldn't see me on this one, but at least we got some work done. All right, so bye bye.